So I'd like to talk today about some work we've been doing using tensor networks, but from a slightly different perspective, not master equations or reduced density matrices, but probably the thing you should never really ever try and do, which is to look at the complete system and environment wave function and compute all of its dynamics. And over the course of this talk, what I want to show you is that using tensor networks, particularly matrix product states, this kind of approach can allow you to get very accurate open system dynamics, so reduced state properties in rather challenging physical scenarios and models. But the kind of overhead of computing the entire system environment wave function isn't just overhead. There's really extremely useful information in the environment part of the state, from which we can actually gain rather rich insight into how non-Markovianity and other things emerge in the reduced density matrices, and particularly when we combine this with models of sort of realistic systems parameterized by sort of ab initio methods, we can actually get some real insight into what the environment is actually doing to sort of drive the open system dynamics. And it also provides a sort of natural framework for thinking about, once we have sort of an idea of what environments can do to systems, particularly when we think about transformations of some kind, to think about how to sort of engineer or exploit environments for potentially desirable purposes, or even vice versa, how the system could be used to drive an environment to do something interesting, something mechanical maybe. So in another change of pace, I thought I would hang all of these sort of ideas on an actual physical example. And that example is the process of singlet fission. So singlet fission is something that happens in organic optoelectronic materials. So in these sort of materials, the primary photo excitations are normally singlet Frankel excitons, so electron hole pairs with no net spin. Now, in organic materials, because of very strong Coulomb interactions, the energy of a singlet exciton is much, much higher than the corresponding triplet excitons, so spin 1 excitons. It can be so much higher, in fact, order of EV in some cases, that it becomes possible for that singlet to, on energetic grounds, decay directly into pairs of triplets. Okay? So, in principle, what this allows is that a single photon that's absorbed by the material could actually give 2 pairs of charge carriers. And so this could be properly integrated into organic photovoltaics. It's been known for a long time that this could allow for efficiencies beyond the famous Schottky-Queisser limit or single bandgap semiconductors. So there's been a lot of interest and work on that, and as I'll show you, you need a lot more than just this sort of simple energetic alignment for fission to happen well. And there's a wide variety of different timescales that are known, raising questions about what is it that controls the efficiency and yield and performance of fission materials. And someone who's worked most of their career on open systems, what's sort of intriguing, interesting for me and my group was the suggestion that it's really the molecular vibrational environment that controls these dynamics. And that it's really a critical factor in getting to good fission materials. Small molecules and sort of more extended polymeric systems. And so with some of our experimental colleagues, we came up with a few sort of models for how we could think about the links between fission and dissipative dynamics, but they were just sort of toy models that allowed us to rationalize some of these sort of ultra-fast optical experiments, 2D spectroscopy, various types of sort of transient absorption. But they're just ideas, they were sort of concepts, and what we really wanted to do is sort of get under the hood of that and look really at a sort of microscopic level about what's going on and what vibrations do in interaction with electronic states. So what we did, let's go looking around for the simplest kind of model we could find that we thought we could do a reasonably complete job on. And our colleagues suggested this dipentacene dimer, so it's a small molecule, which they'd shown undergoes fission in about 200 femtoseconds in solution, and which has the virtue of being small enough that some of our other colleagues from sort of the electronic structure world, Nick Hyde, now in Oxford, Warwick, were able to actually derive a linear vibronic Hamiltonian, which has a sort of open system form. Our system here are the electronic excited states of this molecule. So those are the two Frankel excitons, only one of which is photoactive, can be excited, it's the bright state. A pair of charge transfer excitons, so the electrons and holes live on different molecules. And this triplet pair state, which is the lowest lying eigenstate. Our environment, as said, are the normal modes and vibrations of this dimer. There are 256 of these with a sort of dynamical range spreading femtoseconds to picoseconds. So think about the response functions. These things, it's multi-scale. And it's linear vibronic, and we're going to treat those, our environments, as we've seen many times, many of the different models, as harmonic oscillators. This makes our life a lot easier. Now, from an open system perspective, what's particularly interesting, particularly with this idea that it's the environment that actually drives or controls the fission, is that at the sort of cruciform ground state geometry of this system, all of these electronic levels, our system, are uncoupled. Okay, so for dynamics to happen at all, what we actually need is basically the phonons, and particularly the ones that break symmetries, to become displaced, and this is actually what creates the couplings that allow the system to evolve. So our bath here both creates the couplings and also supplies the bath that allows energy to be dissipated and sort of drive us downhill irreversibly towards the, well, hopefully towards the TT state. So of course we're going to do numerics eventually, so we take D levels, some sort of truncation of these oscillators. And the coupling has this linear form, so similar to what we saw in some of the talks earlier, but with a complexity that I'll come to in a moment. So it's sort of linear in the displacement of the baths. These W's here are transition matrices between all of these different types of excited state. And I'll just mention there's something that's quite common in many fission systems. Even when the molecule is distorted, no direct coupling actually in here ever links the optically excited state with the triplet pairs. They talk to each other at all. It has to be via these CT states, these high line states, which is why we have to include them in the description. Okay. So once we have all of that, the basic goal is to try and understand the fission process, this molecule. Or rather, the task we set ourselves was just to take all of this and just solve the Schrödinger equation for the complete electronic vibrational wave function. Okay, and of course, you know, this seems like a kind of a foolhardy kind of endeavor, because immediately we encounter the recursive dimensionality. If I try and write just a complete wave function like this, the number of parameters just explodes exponentially.
Can I clarify something?
Yeah.
So the way you've drawn this, if these are electronic eigenstates,
Yeah.
then by definition they're never coupled, because they're the eigenstates of the electronic Hamiltonian. They're never coupled without the vibrations.
Yeah.
So are you saying something more than that? Because this will be true for any system if you.
No, that's absolutely right. So I mean, this is a TD-DFT thing. So they fix a geometry and they just diagonalize that geometry. So of course they're eigenstates, and then yes, you need to have.
Like for any
you need to move
system.
on a surface to start to couple them.
Yes. So for any system you're looking at a relaxation of eigenstates, you need vibrations, otherwise the eigenstates.
Absolutely. I suppose I was just constant. And we'll sort of see this when I sort of show how the fission occurs. But when we think about some of the models we saw before, like the spin boson model and other things, there are couplings already in the systems of Hamiltonian, and then a coupling to the bath.
Because you're not starting with an eigenstate.
Oh yeah, sure. No, of course, I agree, absolutely. just with a sort of mixed audience where they might be used to having sort of a starting Hamiltonian that has couplings, and you don't start in an eigenstate basis necessarily. I just thought I'd just say that. But no, absolutely. I mean, this is these are just the we're going to use a diabatic basis, but at this geometry, these are the adiabatic states as well. Okay, so this doesn't look like an easy thing to do necessarily. But as I said, this kind of Hamiltonian has this sort of open system structure, and over the last 10-ish years, we've worked a lot on using matrix product states to try and simulate these open system kind of problems. And we sort of have some intuition that, that we shouldn't need all of these amplitudes. We have a sort of central system strongly coupled with all of these individual modes. They themselves are sort of non-interacting. So you could sort of imagine that, well, entanglement between system and these modes could be strong. Between the actual modes themselves, it's likely to be rather weak. So if I start the dynamics at some particular point, and often for open systems, this is a product state, simple product state. This Hamiltonian is not going to take us very far. So there should be some sort of ansatz with far fewer parameters that should allow us to do the complete dynamics. And the form of that ansatz, which I think is going to be no surprise, becomes sort of evident from when you realize that this kind of central problem, so this is the kind of Hamiltonian that Peter and Nancy were sort of showing earlier. If you have this kind of factorized form and some arbitrary spectral density describing the distribution of couplings, it's always possible to perform a unitary transformation of the environment modes such that this problem is exactly transformed to an equivalent problem where your system just couples to one end of a semi-infinite chain of oscillators that have strictly nearest neighbor couplings. It's kind of tridiagonalization, really. But of course, that kind of Hamiltonian has it's 1D, short range, and so it's well known in these, as long as they're gaps, that they have formally limited entanglement and non-extensive entanglement content. And they can be very, very efficiently described statically, ground states, and dynamics by matrix product states. So over a number of years, the combination of being able to take open system problems, non-perturbative or Markovian ones, map them onto these sort of chain-like problems, basically opens up the ability to use all of the sort of power of NPS time-dependent methods that have been developed elsewhere to look at a range of open system problems. And that sort of led basically from about this time when I was working with Martin Plenio and Suzanne Wilder in Ulm to the time-evolving density with orthogonal polynomials algorithm, which we've applied to a range of non-perturbative open system problems, spin boson model, quantum impurity problems. Someone mentioned the FMO before, so photosynthetic complexes, superconducting circuits, which I think it's actually the paper that Peter had on his slides. And so we thought we could probably have a go at this fission problem in this kind of format. Now, sting in the tail for this molecular problem starts here. If you have this kind of interaction, this unitary transformation into a chain is easy to do. But the actual interactions we have from the ab initio data don't factorize. The matrices, in principle, are different for each and every vibrational mode. We often talk about a full rank interaction there. And if we can't make this factorization, we can't really just make a simple transformation onto the chain. There's no reduction there into a kind of cheap and easy to do format. So that looked like a problem. But then what we actually tried to do, or one of the students did, was try to sort of make a generalization of this and try and actually look at the pattern of these couplings to try and group them against some sort of common operators. The way he actually did this was to use something called k-means sort of learning algorithm. So it just analyzes these data, searches for all the modes that have the same sort of matrix up to a constant of proportionality, which is essentially what this form is. And when we did that on this particular problem, so we have all of these different types of coupling, we found that actually this thing actually does break up very naturally into a smaller number of sub-environments, each of which then can be transformed into a chain that we can deal with. But the complexity sort of does grow because we have 7 environments. We have something more like a tensor tree structure to deal with in this particular problem. Okay. Now, the fact that this set of matrices breaks up into a smallish number of sub-environments is no accident really. And we're probably going to save ourselves a lot of bother by just looking just at the symmetries of the original molecule at this cruciform geometry. So this has a D2D point group. So basically all of the electronic states and all the vibrations can be labeled by the different IREPs of this group. Okay. And there are 4 of them. So the environments naturally break up into 4 groups. Okay, and each one, by the sort of symmetry selection rules, only couples in a certain way between certain states, so that E2 nodes couple these guys, not the others. And so this sub-environment structure was sort of always there, and we probably could have just started there if we knew anything about chemistry, but by not doing that, we need some consolation that this search method sort of does the right thing. Okay, so we now have a tensor tree problem to deal with. And from there, we can just write this as a tensor tree ANZAT. So most of the environments just look like the normal 1D MPS. Okay, they're no more complicated. The only thing that's different now is just our parent node, which is the system tensor of this tree, is multi-dimensional. In this case, it's 8-dimensional. To do the actual time evolution, we've always worked a lot with the one-site time-dependent variational principle. We've got an ANZATS. We can apply Dirac-Frenkel time-dependent variational principle to derive equations of motion for the tensors. So well-known, well-established technique now. We like one-site TDVP for this because we're actually dealing with tensors where the local Hilbert space can be large. They're harmonic oscillators, and so we get a useful speed up by dealing with one side problem because this is essentially linear scaling in D. When you go to 2 sides or other things, it gives D squared. And also just being a one-side method, I've only shown 2 branches of the tree. There's a very sort of simple management of the update sweeps with this. You know, we just go around all of the different branches updating in each time sweep. And I'll just sort of mention another thing that the original 1 TDVPs tended to be dynamics at a fixed bond dimension. It works on a manifold into the tangent space of manifold of states at fixed D. So you would run dynamics at some D and then run them again and again and again, different higher Ds, high bond dimensions, until some sort of convergence criteria is met. More recently, we and actually quite a few other people managed to sort of derive ways of doing bond adaptive one-site TDVP. So you can retain those one-site numerical advantages, but the bond dimensions will just grow as needed, again, according to some criterion of precision, during the dynamics themselves. So you don't need to do all of these different runs anymore, which is particularly useful when you start from a simple product state, because previously you'd have to just sort of we've got rather simple low entanglement dynamics at the beginning, but you'd have to embed it in some large D to get out to large times. And now you don't have to do that. So we set all of that up. We sort of simplified and sort of tamed our full rank, or well, it wasn't full rank, but more complicated environmental interaction. And had the ansatz equations of motion, and so just time to simulate. So we hit play, and we sort of immediately hit a wall, essentially. Having simplified that problem, what we actually found now was essentially a problem at the system environment interface. So this thing now has all of 7 sort of dimensions. Number of parameters is number of states in the system, and the bond dimension to the power of all the stuff that's coming out of it. And it is precisely the system environment interface, or we would expect the largest bond dimensions to be needed. That's really where all the system environment entanglement is sort of localized. And so that sort of became a problem for us. And so we couldn't actually even run the simulations very long. We could run them for a while, just sort of have an idea of where they were going, but we certainly couldn't get far enough into the dynamics to even really talk meaningfully about fission, and that was the original idea. So, what do we do? Well, I mean, just as we sort of took the original full configuration wave function, thought about how we could decompose it into matrix product states. We took sort of a high-ish rank environmental interaction and broke it up into subsectors. The notion here is we've got a big object, high dimensional. Let's just try and break it up again into smaller, simpler, easier to use objects. And so Florian Schroeder was the PhD student, inspired by ideas of entanglement renormalization and the idea of actually bringing in, essentially sort of doing data compression on this large system tensor. Performance correlation analysis, we look at sort of the mutual entropy between different degrees of freedom sticking out of this thing. And when we see they could actually potentially be compressed, this thing being smaller than some of these guys, we join them together through an artificial node of this thing. And then perform this all the way around here, joining things up with all of these objects that are at most 3-legged or 3-dimensional. So we don't get this, some of these horrible numbers that appear up here. And so, or I should have said that, and that was based on the early time dynamics, just seeing where everything was building up and then decomposing it. Then we take that new network as a new starting ansatz, and then just start running the dynamics again. And this time, we found a huge amount of compression, and we were able to actually run the dynamics from singular exciton all the way down to complete fission. And basically we now have a sort of slightly different type of tree network with this extra layer here, which, okay, I'll just mention this here, but it has some similarity to what's done in multi-layer time-dependent, multi-configuration or time-dependent hard tree type approaches, but the exact connection is not necessarily clear to me. All right, okay, so that's kind of like how the problem was sort of like tamed with this sort of space of methods. Here are the results. So 1, the fission happens, which is a big relief after all of that. So we have here the populations of the various excited states. Start with the brightest excited singlet, it decays, triplet pairs appear, and they appear, it's sort of testament to the abolition modeling on a timescale that's tolerably close to 200 femtoseconds. Okay, great, but what do we actually learn about how the fission is happening? in addition to just this rise and down, we see sort of there are other scales here. There's this fast stuff where the bright exciton mixes with the dark exciton, other sort of transient dynamics, and of course, sort of as promised, we can look into the environment and look at where all of the what's being excited in these different chains of environments, and these distinct different sort of symmetry labeled environments all light up at different times, broadly corresponding to moments when things are happening in the electronic state. So this is how we kind of see fission happening as a sort of three-stage process. The first thing that happens, we excite in this sort of period here where we get this strong mixing. It's the B2 modes which couple these two states that light up on sort of tens of femtosecond timescales, and it's causing this. But this isn't actually energy exchange. The LE state is actually plus minus, of course. Is lower in energy than this guy. This is just very strong coupling between these modes, which causes them to just mix and change characters. So as these modes get displaced, adiabatically, this state kind of moves to here and changes its character. It acquires now LE plus and LE minus character. Okay, that's the nature of our photo excitation has changed due to the environment displacement. What's important for that, or what's important about that process happening, is the LE minus character is coupled by B1 modes to the CT states, and it's the same B1 modes that are coupled down to the TT. And the fact that they're the same modes makes it possible for essentially these double couplings to create coherent vibronic super exchange between lower manifolds. Okay, and so you see now when the red and the yellow start to co-decay, because this is really kind of like the excitation. TT comes up and the B1 modes start to rise, and you also see a little bit of this sort of virtual population of the CT, of these high-lying CT states. They're not really ever really populated, and that creates a mixing between these two states, which allows then dissipation, now incoherent emission into the remaining, the symmetric type of environments, to take us from this sort of upper state down to this state. So this is sort of non-adiabatic dynamics. Final stage is that once we've sort of collected down here, because they're coupled, the TT and the LE state still slightly mixed. But now reorganization dynamics, so the sort of symmetric modes, which can change the relative energy ordering of the levels, kicks in and starts to drag this thing down, demixing it, decoupling it, purifying it, its nature to become purely TT, and that's all this slow stuff. So here you have something that looks kind of more exponential, and then like all of these tails, this is the last stage of this thing is just energy relaxation. Well, the energy levels are moving to lower energy and decoupling from each other. Okay, so I mean, I guess I use this example because I just wanted to show you how we can use the information in the environment to sort of tell a story and understand things that we might not necessarily get just from looking at these populations. If I only had this, I'd probably just say, okay, the whole story is 200 femtoseconds, and that's it. And there's a clear sequence, I mean, just so now like at a sort of concept level of how I think it's interesting to think about environments as capable, particularly if they're multi-scale. The first process goes fast because those modes are fast. Okay, and then the last stuff is slow because those modes are slow. And each one, because of the complexity of the coupling structure, does different things to our system, changes how they subsequently interact with other environments down the line. And so from an engineering principle, it's maybe interesting to think about the design of environments in that way, if you want to actually achieve something. I mean, there's sort of many sort of examples, some examples where this is positive set occur in, for example, proteins, which have dynamical ranges going from femtoseconds down to milliseconds, and they're capable of performing extremely advanced transformations of excited states and excitations. And also, just as theorists, just order is clearly important, and something we can do as theorists, and so easy in the experiments, is we can sort of take out some of these intermediate steps. So if we knock out this path, or this step, we just take that environment out, fission will still happen, but it happens by a completely different set of processes in different environments, and it's much slower and lower yield. So you sort of almost think about sort of doing theoretical type of path engineering, exploring these things. You could have done it the other way. We had the slower one, we could try to find the fast one. Okay, how am I doing for time?
10 minutes more, including, well, 15 minutes more, including questions.
All right, well, actually, I might bring it in on time. So another quick set of things we can do with all of the bath information, and of course with the ab initio modeling, we know exactly what the normal modes actually are. So when a certain mode is excited, I can tell you what it's actually doing in real space. Is that we'll sort of just trace the electronic system and look at the bath dynamics and do that information about normal modes, turn it into a kind of molecular dynamics, where I was mentioned earlier on, we're doing the full quantum mechanical problem for the electronic state. So we have sort of non-adiabatic forces and the whole sort of business. So we can start making movies like this. I mean, this is potentially of interest if you want to think about how we control mechanical motion of molecules, machines, little things like that. I mean, at some point in this video, this thing starts to really show some sort of piston-like pumping, but you could imagine in a more complicated model, ring openings, twisting, rotations, whatever you want, on the basis of exact photo response to the electronic sort of states. I mean, that's just at the moment just a bit of fun. This particular molecule, what we could do here is go back to that original basis before we turned everything into chains and look at, well, what are the actual normal modes that contribute most to the dynamics in those particular different phases, and from those predictions we can compare things like ultra-fast impulsive Raman, so pump probe, where you pump the system and let some little time delay happen, and then do a Raman experiment. This actually allows you to actually look at the Raman signatures and vibrational coherences on different excited states rather than just the usual. And by varying that time delay, you can have a look at vibrational coherences, for example, on the TT sort of product state, shortly after they've been formed by these various pathways that I showed, or just at some very long time where everything about how it was formed has in principle gone away. And so when they basically cuts through this spectrum in the experiments, these modes here, if you look at the sort of long time static TT type Raman spectrum, they're not there. If you shorten the delay to times where you can see things that have been carried over, particularly vibrational coherences, so you can see a lot of this ringing on symmetric surfaces that appears at that long time, are still there. They pick them up in sort of different okay-ish job. We've got these two guys and plus some other stuff not seen.
So do you include the solvent effect?
Sorry?
So are there solvent effects included in your calculation?
Only indirectly, in that there's, when we turn these things into chains, we have a certain number of normal modes representing that, and so that wouldn't include any solvent effects. So there's, and it's a pure wave function method, so you can't damp them like you would in a master equation. However, what we can actually do is add extra sites to the end of the chain, allowing things to sort of leak out, and this has the effect of sort of adding like a micro environment, but this is actually done. This is not an accurate representation of exactly what the solvent is doing. I'll show you some solvent stuff in a second. Get there.
So is this 0 temperature?
So this stuff was at 0 temperature, but we can do finite temperatures. And what I'll do is I'll skip ahead and show you both something, if that's okay. Okay, so yeah, so it seems to sort of work out okay with my experiments. This is sort of work in progress. We had a sort of first go at it here, but often in chemistry problems, people like to see dynamics running on potential energy surfaces. Ways of thinking about dynamics is in terms of wave packets moving on sort of Born-Oppenheimer type surfaces. Here, we had 256 sort of modes, and it wasn't, I don't even like 3D movies, so like thinking about like some thing in 200 dimensions would be like crazy. But every time, and we use the Schmidt decomposition to actually do the dynamics. If you just make a bath environment split, particularly in this particular problem, you get 5 states, okay, where you have the system degree of a system state is associated with some many-body environment state. And so the idea here was just sort of at every time. So we can't visualize everything in 256 dimensions, but we could do them in the one dimension that we do have, which is time. And so we can take these configurations and use them to, well, either we subtract off the nuclear kinetic energy and then diagonalize the system Hamiltonian to get sets of system eigenstates at certain path configurations at each time step. So then we can start to think about not just looking at populations and basic properties of the system, we can also look at their unoccupied states as well, and look at how this spectrum leads to dynamics. So we can also do this including non-adiabatic couplings. Turns out essentially to be the effective Hamiltonian 1 TdEB. And here, just very quickly, this is a bit like we started on the upper surface. As we go along, this non-adiabatic or decay from that surface down onto the lower surface. That's one way of seeing fission here. On these surfaces, it actually appears as a avoided crossing phenomenon. The unoccupied TT state here goes up in energy through here. Those B1 modes haven't been activated yet, so this is a real crossing. And then as those B1 modes get activated, it gets pushed down, it comes through here, coupling is turned on, and if you like, this lower state just changes character into the TT state continuously. Okay. So yeah, so that's some of, just to give you an idea of our thinking about what we can get out of the environmental parts of this approach to open system dynamics. We've carried on, and everything I've sort of shown you and will show you has, over the last couple of years, been sort of added to this Julia package, which is freely available. And we've carried on with this sort of idea of exploring what we can get from environment. So one recent example is just looking at heat flow from between 2 environments, and actually looking at how, as they go through us into the quantum junction, broad ideas about thermodynamics here. That's something that one can do and actually sort of measure what's actually happening in the bath. These are actually currents flowing through here, as I drive the system or do something transient there. To answer your question about how is this done with a pure wave function, right? Because you mentioned, of course, sampling. This would become nightmarish if we had to run lots and lots of samples of these big wave functions. There's a very nice trick developed about 4 years ago that shows that it's related to what they would call the thermofield transfer. And so it turns out that there's even a nicer variant of it. Thermofield normally requires to double the size of the environment. It's really nice theorem that says that in fact you can do the same thing with just a single environment but at a modified spectral density. So all the temperature details go into there. Nothing is free. This new single environment contains negative frequency modes, which one should always be careful with. But in all the cases we've tried it, and we've got a lot of recent paper just really looking at how exactly that works. It works, or at least it's worked for us in the cases we've looked at. But it's based on that sort of thermofield kind of idea. Okay, just a few other things. Again, this is ab initio work where we're just looking at the role of conical intersections and absorption and emission spectra. Here, what's really important is just that the different environments, here they've already been turned into chains, aren't independent. There are strong correlations that need to be included in order to get the spectra right, which translates into having long-range interactions. But again, sort of variants of 1 TDVP that we've been using seem to handle these just okay. So that's work with Christina Isborn and Tim Zulsdorf, Oregon, said. Some work on organic claritons. If you want to see what's coming out of the cavity here, we would actually just include that as an environment and just measure where the energy is going in real time. You'll also have a look at relaxation from the upper clariton to the lower clariton, for example. So we can do sort of spectroscopy in a way by just looking into our environment. In Peter's talk, he sort of spoke about systems that interact in an environment through space. We actually bring the space degree of freedom into the description, and rather similarly, we can sort of look into the environment, see how signals, energy, potentially information, are exchanged between systems in time, that's space, see recurrences, and various other things. And yeah, that's it. So just basically a recapitulation of what I said at the beginning. I guess the main thing I just want to get at is, why are we doing this? Why are we doing this to ourselves? The idea is to think about really the use of environments in the long run to do multi-particle correlated stuff across different timescales, from physics to chemistry. It's like over nanometers. Biological systems are good at this. And we want to be able to set up the tools to be able to kind of think about doing that ourselves. Think about people, and thank you for your time and patience, I should say. Thank you.
In the animation you showed, was that just an illustration? Because I don't understand how you would go from wave function to atomic coordinates, and also how you go from normal modes to full Cartesian coordinates.
Right. Okay. So there's a fixed. So the short answer is what we would do there is, or what we did is. Yeah, that's right. Compute just the displacements of all of the different normal modes during the dynamics, and just feed them into, for a given displacement if you know the pattern of atomic displacements.
But you
Do-
have a
do
wave
that.
function. How do you just get display? You just compute a wave function, right?
We just compute the wave function. Yeah, okay, no, so the picture is based on observables. So we go away from the wave function and just compute what each normal mode is doing at some time on average somehow.
But
And-
the wave function will split on the various diabatic surfaces, right? It's not localized. So how do you calculate?
So I mean, I showed an example where there was, pure kind of bifurcation of the wave packet. That in some sense gets averaged over in some sense. So if you have a wave packet that does this, in the movie I sort of made, it would say that that's not very strongly displaced. Whereas, of course, in the real thing, you should pick one or the other. So what we need to do is actually add something that actually decoheres the system a bit more. So, like I said, it's just at the moment it's not something seriously for molecular dynamics, but it is something we want to try.
I don't think it's the coherence. It is that the wave function is going to split as it transfers from one state to another.
Yes.
So to split over all the states.
Yes.
So you're going to have density on all the states. So
Yes.
I don't understand.
So then we just trace all of the over the states to get some sort of average of what the molecule is doing on any of the surfaces at any time. And you just trace them all the way through and just get a reduced density, exactly, which includes on one surface the wave packets over here. There's another thing there where you think it takes a kind of average of that.
And how
So
do you
you're
go-
kind of showing the exact mean field trajectory.
Effectively, yeah,
Yeah,
it
where
should-
you have
it
the
should-
mean field trajectory taken from an exact wave function.
Yes.
And how do you go from normal modes to full Cartesian coordinates? Normal modes is 3n, sorry, Cartesian is 3n, normal modes is 3n minus 6. So you have the 3n minus 6 information about the 3n minus 6. How do you go to 3n?
Do we have the three and minus? Oh, I see. what
The
you mean.
normal
Okay.
modes.
Normal modes. Okay, so yeah, so we've just bolted it down. There's no chance for it to have the motions with rotation and translation and the other. Is that
How do you extract Cartesian coordinates, which are 3n, from the information about the 3n minus 6?
So if I just decide that okay, so it's
So
not.
you get those average positions, right? 3n minus 6
Yeah.
from them.
No, so okay, so essentially what we're going to do is like take the cruciform ground state geometry and fix it in some sort of lab right now, and then just have the 3n stuff on top of something that otherwise can't explore those other six translations and three translations, three rotations. So, no, I agree with you. It's something. We're only looking at the internal coordinates, and I've just fixed it to not to explore those 6 degrees of freedom somehow. Perhaps
Yeah,
we
it's
could-
difficult to
yeah.
find. We can discuss it later.
And this is kind of a sort of bit of a general question for someone who's talked about things on the border of chemistry, and maybe Nancy might comment on this too. We all like these kind of models of electronic states coupled to bats of harmonic oscillators. At what point can't you do that? What sort of physics? I mean, certainly even in things like this, are there potential points maybe for anharmonic dynamics and things like that that are excluded that might be important, or something else where you
Yeah. So anharmonicities is hugely important for some real systems and particularly perhaps longer time things as well. where anharmonicity is maybe like important, we have the sort of only approach we've really found for that is sort of take them out of the description of the environment and include them as real coordinate particles with potentials and in the system, and that kind of gets like a big problem kind of quickly. And
is there any possibility that this singlet fission process depends on that? But in the real world.
so I think, I mean, it probably is because, like in that experiment, the fact that when the fission happens and there's some vibration, there's dynamics. If you're just harmonic and sort of almost like a close system, they hang around for ages. You know, there should be also something that allows the environment to redistribute energy amongst itself.
I mean, I'm sort of happy with the answer, maybe, right? I mean, it's very nice that you've been able to model this at all. So I'm not suggesting you should go and put that on Steve. Thanks.
Are there other questions?
So have you compared your results with simpler, maybe second order dynamics equations?
So I wonder how important
Whether it's really in strong coupling regime and how important the non-Markovian effects are for the singular fission. Yeah.
So we didn't really compare it to just like a simple master equation. But there was the sort of reason for that was in some other context here was actually sort of told the story backwards. Actually, we kind of had the experiments with like showing all the particular vibrations first. So that was always what we had in mind. And of course, I suppose we could have done the master equation just to see if, you know, maybe that's not important and you get 200 femtoseconds just from that. But we actually wanted the modes somehow. But we could, yeah. I mean, well, we should have.
Any other questions? One last question.
What is the solvent in this system? And sort of in particular, is it that polar?
No,
Okay.
I think it's a cyclohexane or something like this. Some of the other dimers, we did some work where they changed polarity, and this is really important for those CT states because they obviously have dipoles, so you can really change where they sit energetically with in solvent polarity, and you get all sorts of different types of fission behavior. That was in another system. So this one's just not perfect.
Okay, so let's thank Alex again.